Every year, China tears itself down and builds itself back up. As old districts fall to make room for new towers, the country generates an estimated 2 billion tons of construction and demolition waste annually, more than any other nation on Earth. Picture that figure not as a statistic, but as a physical thing. A rising range of shattered concrete, splintered brick, twisted rebar, and pulverized mortar, spreading across the edges of nearly every major city. For decades, this material had one destination. It was trucked to informal dumps, buried in landfills, or piled into unauthorized heaps that swallowed farmland and choked riverbanks. Beijing alone was producing tens of millions of tons a year at the peak of its redevelopment. Shanghai, Shenzhen, Guangzhou each fed the same growing mountains. The problem was not simply volume. It was contradiction. China was importing sand and quarrying virgin stone at enormous scale to feed its concrete demand, even as it dumped the crushed remains of yesterday's buildings just kilometers away. The raw material was already there, sitting in the rubble, and the country was throwing it away twice, once when it demolished, and again when it dug fresh aggregate out of the ground. Somewhere in the last decade, that contradiction became too expensive to ignore. Land for dumping ran short, environmental inspectors grew stricter, and engineers began asking a simple question. What if the Mountain of Rubble was not garbage at all, but a quarry that had already been mined? This is the story of how a nation drowning in its own concrete began treating demolition waste as a resource. It is a story of crushing machines and quality standards, of national policies rewritten in 2025, of recycled blocks and printed houses, and of the viral claims that have wildly outrun the verified facts. Because alongside the genuine engineering breakthroughs runs a parallel current of exaggeration. The idea that China is now printing entire homes from pure industrial waste in a matter of hours. Some of that is real, much of it is not. To separate the two, we have to start at the bottom of the pile and understand exactly what construction waste actually is. Demolition debris looks like chaos, but it is not random. Break open a typical load of Chinese construction waste, and you find a predictable mix. The largest fraction, often more than half by weight, is old concrete, hardened cement bound around sand and crushed stone. Next comes brick and clay masonry, then mortar and plaster, then ceramic tile from bathrooms and kitchens. Threaded through all of it is steel, reinforcing bars, mesh, wire, and fixtures. Add fragments of glass, wood, insulation, plastic pipe, and gypsum board, and you have the anatomy of a demolished building. Each component behaves differently, and that is precisely why the mixture was historically so hard to reuse. Concrete and brick are strong in compression, but must be crushed and sorted to be useful again. Steel is valuable and magnetic, so it can be pulled out and sold to scrap mills. But the contaminants are the trouble. Gypsum releases sulfates that can attack fresh concrete. Wood and plastic rot or weaken any mix they enter. Old mortar clings stubbornly to concrete fragments, coating them in a weak, porous shell. Separating a clean stream of reusable stone from this tangle takes deliberate processing, and for decades, nobody in China had the incentive to bother. Virgin aggregate was cheap. Labor to sort waste was expensive. Landfill fees were minimal or unenforced, so the debris was simply hauled away, mixed and unsorted, and dumped. A demolished apartment block that contained thousands of tons of perfectly crushable concrete became 1,000 tons of pure waste the moment the wrecking ball struck. The material's value was destroyed not by demolition, but by neglect. Understanding this composition matters, because it defines both the promise and the limit of recycling. The concrete and brick fraction, the bulk of the pile, can genuinely be reborn as new building material. The rest must be filtered out. The entire recycled construction industry hinges on how cleanly and cheaply that separation can be achieved, and how strong the resulting product turns out to be. So the real question becomes mechanical. How do you take a mountain of mixed rubble and turn it back into something a builder would trust? The answer begins with crushing. The transformation starts with force. At a modern recycling facility, mixed demolition waste is fed by loader into a primary jaw crusher, two heavy steel plates that grind together, breaking large concrete chunks into fist-sized fragments. From there, the material rides conveyor belts through a sequence of stages. Magnetic separators sweep overhead, plucking out reinforcing steel by the ton. Vibrating screens sort the flow by size, sending oversized pieces back for a second pass through impact crushers that further reduce and shape them. Air classifiers and water baths float away the light contaminants, wood, plastic, paper, while the dense stone sinks and is collected. What emerges at the end is recycled aggregate, graded piles of crushed material sorted into coarse and fine fractions, resembling the gravel and sand a builder would otherwise buy from a quarry. The best facilities process hundreds of tons per hour, running mobile crushing plants directly at demolition sites to avoid hauling costs. Others operate as fixed regional centers, receiving trucked-in debris from across a city. Until recently, the quality of this equipment, and of what it produced, varied enormously. A cheap crusher with poor screening could turn out aggregate laced with mortar dust and contaminants, undermining trust in the entire product. That is what China's new technical standards, taking effect across 2025 and 2026, are designed to fix. The rules specify requirements for recycling equipment, crushing efficiency, separation performance, dust control, and the consistency of output. Parallel standards govern the aggregate itself, setting limits on impurity content, water absorption, particle shape, and strength grade. The intent is to move recycled aggregate from an informal, buyer beware commodity into a certified, specification-grade material that engineers can design around with confidence. Standardization is the quiet revolution here. A crushed stone that no one can measure is worthless. A crushed stone with a documented grade and predictable performance becomes a substitute for virgin material. By defining what the machines must do and what the product must meet, China is attempting to industrialize what was once a scrapyard trade. But standards reveal an uncomfortable truth as well. When you test recycled aggregate against fresh quarried stone, it is frequently weaker, and that weakness is the next obstacle engineers must overcome. Recycled aggregate carries a hidden flaw, and it comes from its own history. When old concrete is crushed, each new stone fragment is wrapped in a layer of the original cement mortar. That mortar is porous, cracked, and full of microscopic voids. It absorbs water like a sponge. Recycled aggregate can soak up 5 to 10% of its weight, compared to 1 or 2% for virgin stone. It is also mechanically weaker, so the crushed particles fracture more easily under load. Pour this material into new concrete without adjustment, and the result is predictable: lower compressive strength, reduced durability, and greater shrinkage as the mix dries. Laboratory tests routinely show recycled aggregate concrete performing 10 to 30% below an equivalent mix made with fresh stone. That gap is the central engineering challenge of the entire industry. Engineers have developed several answers. The simplest is substitution ratio, replacing only 20, 30, or 50% of the virgin aggregate with recycled material, keeping the weakness diluted within acceptable limits. Another approach strengthens the aggregate itself, treating the crushed particles to remove or seal the clinging mortar, or coating them with mineral additives that fill their pores. Mix designers also compensate by lowering the water-to-cement ratio, adding fly ash or silica fume, and using superplasticizers to keep the concrete workable without weakening it. With careful control, recycled aggregate concrete can be pushed to structural grade, strong enough for beams and columns. But here lies the crucial distinction the industry does not always advertise. What a laboratory can achieve under controlled conditions is not the same as what appears on an ordinary construction site. Lab-grade recycled concrete, made from clean, single-source, well-processed aggregate, can genuinely rival virgin material. Site-grade recycled material, produced from mixed debris of unknown origin, is far more variable, and is usually steered toward less demanding uses. It becomes road subbase, backfill, pavement layers, and the raw material for non-structural blocks and bricks. That is not a failure. It is honest engineering, matching material quality to the job it can safely perform. Understanding this divide protects us from the hype that follows. Because in 2025, a wave of national policy suddenly pushed enormous volumes of this material into use, whether the market was ready or not. For years, recycling construction waste in China was possible but unprofitable. The virgin alternative was cheap, and no one was compelled to change. In 2025, that calculation shifted, not through invention, but through policy. National directives set a concrete, measurable target. Prefecture-level cities were to raise their construction waste utilization rate above 50% by 2027. That single number reorganized an entire industry. A utilization target is a blunt but powerful instrument. It means a city can no longer simply bury or stockpile its demolition debris. A documented share of it must be processed and put back into use. Local governments, held accountable for the figure, suddenly had reason to license recycling plants, allocate land for processing centers, and steer public projects toward recycled products. Roads, sidewalks, riverbank reinforcement, and government construction became guaranteed buyers for recycled aggregate and blocks, creating the stable demand that private recyclers had always lacked. The policy did not act alone. It arrived alongside the technical standards taking effect in 2025 and 2026, which defined equipment performance and aggregate quality. Together, target and standard formed a system. The target created demand. The standards ensured that what was supplied could be trusted. Financial mechanisms reinforced both: subsidies for recycling facilities, preferential treatment in public procurement, and penalties for illegal dumping that made the old shortcut expensive. For the first time, the full economic chain pointed in one direction: waste in, certified material out, guaranteed buyer at the end. The effect has been to industrialize a trade that was once informal and fragmented. Mobile crushing plants now appear at major demolition sites. Regional recycling centers process debris by the millions of tons. Cities publish utilization figures as performance metrics. Whether every city genuinely hits the 50% threshold by 2027 remains to be verified. Targets and reported numbers are not always the same thing, but the structural pressure is real and pointed firmly toward reuse. This is where recycled construction stops being an environmental slogan and becomes an economic engine. The rubble now has a market, a price, and a legal reason to exist. And once that market was secured, the crushed aggregate could finally become something a builder would recognize. Not just gravel in a pile, but blocks, panels, and paved roads. The question was, what, exactly, China was building from it. Recycled aggregate rarely ends its journey as a loose pile of gravel. Instead, it feeds a second industry that reshapes the crushed debris into finished products. The most common destination is the humble concrete block. Machines mix recycled aggregate with cement, water, and additives, then press the slurry into molds under vibration and pressure. Out come hollow blocks, paving bricks and partition units, gray, dense, and functional. Because these products carry compressive loads rather than structural spans, they tolerate the slightly weaker aggregate that engineers worried about earlier. Road base is another major outlet. Beneath highways and city streets, layers of compacted, recycled aggregate replace virgin crushed stone, absorbing enormous tonnages of processed waste where surface strength matters less than bulk and drainage. Prefabricated panels represent the higher value tier. In factories across Guangdong, Jiangsu, and Hebei, recycled content concrete is cast into wall panels, floor slabs, and staircase units, cured under controlled temperature, then trucked to sites for rapid assembly. These panels must meet the same aggregate quality standards taking effect in 2025 and 2026, so producers blend recycled and virgin material in carefully measured ratios, often capping recycled content at 30 to 50% for load-bearing elements. Verified projects anchor these claims. In Beijing, the redevelopment of demolished neighborhoods has produced recycled bricks used in landscaping walls and pedestrian paving. In Shenzhen, construction waste recycling plants supply road subbase for municipal projects with documented material traceability. Xiongnu area, the planned city rising south of Beijing, has piloted recycled aggregate in non-structural concrete and site backfill, tracking utilization rates against national targets. What unites these examples is documentation, batch testing, mixed records, and project-level reporting that distinguishes genuine recycled content from marketing language. A block advertised as eco-friendly means little without a percentage and a test certificate behind it. The honest picture is incremental. Recycled material is entering the supply chain steadily, product by product, project by project, rather than replacing virgin stone overnight. And yet, one category of construction generates more excitement and more confusion than any block or panel. It involves nozzles, not molds, and machines that build walls layer by layer without human hands. To understand where recycled material fits, we travel to Shanghai. In 2022, a two-story building rose in Shanghai's Baoshan district in roughly 50 hours of printing time. There were no bricklayers stacking courses, no carpenters framing walls. Instead, a robotic arm mounted on a gantry extruded a cement-based mixture layer upon layer, tracing the building's outline like a machine drawing in 3 dimensions. The structure, developed with technology from Tsinghua University researchers and construction printing firms, became a showcase for what automated construction could achieve at building scale rather than in laboratory demonstrations. The process, called contour crafting or 3D construction printing, works by pumping a specially formulated concrete through a movable nozzle. The mixture must be stiff enough to hold its shape immediately, yet fluid enough to bond with the layer beneath. Each pass deposits a ridged bead of material. Hundreds of passes build the walls. Openings for windows and doors are programmed into the design, and the printer simply skips those regions. What printing does well is speed and geometry. Curved walls that would demand expensive custom formwork become trivial for a machine following coordinates. Labor requirements drop sharply, and material waste from cutting and offcuts nearly disappears because the printer deposits only what the design specifies. For repetitive structures, walls, benches, small pavilions, the efficiency is real and measurable. But printing has firm limits. The extruded concrete forms walls, not everything. Foundations are typically poured conventionally. Steel reinforcement, essential for tension and seismic performance, cannot yet be printed continuously alongside the concrete, so rebar is often inserted manually or the design avoids heavy structural loads. Multi-story buildings require careful engineering because printed layers bond weakly across the horizontal seams. Roofs, plumbing, wiring, and windows are all installed by traditional trades after the printer finishes. The Shanghai building was genuine and impressive, but it was a demonstration of automated construction, not proof that houses can be conjured whole from a hopper of waste. The printing mixture was engineered concrete, formulated for extrusion, with its own strict material requirements. Which brings us to the gap between what these machines actually printed and what the internet claimed they printed, a gap wide enough to swallow the truth. Search online for China's printed houses and you will find a recurring headline: entire homes conjured from industrial waste, buildings printed 100% from crushed rubble and factory byproducts. It is a satisfying story, waste in, house out, and it is largely false. The confusion begins by merging two separate innovations. Recycled construction waste is real. 3D construction printing is real. But they are not the same project, and they rarely overlap completely. The Shanghai building was printed from an engineered cement mixture designed for extrusion, not from a hopper of demolished concrete. Printing mixtures demand precise particle size, controlled water content, and consistent flow. Raw, crushed rubble, with its brick fragments, mortar dust, and variable strength, would clog nozzles and produce unreliable layers. Some printing feedstocks do incorporate a fraction of recycled aggregate or industrial byproducts, like fly ash and slag, materials genuinely diverted from waste streams. But a fraction is not the whole. When a video claims a house is made entirely from industrial waste, it collapses a partial, carefully engineered recycled content into a total, and it ignores the cement binder, the additives, the reinforcement, and the conventionally built foundation. The viral version also inflates speed and permanence. A 50-hour print time refers to the printing of walls, not to a finished, inhabitable, code-approved home. Installation of roofing, utilities, insulation, and finishing continues for weeks afterward. Demonstration structures are frequently that. Demonstrations, not certified residences occupied by families. The honest record is more modest and more durable. Recycled material is entering blocks, road base, and panels with documented percentages. Printing is accelerating specific construction tasks. Fly ash and slag are legitimately reducing virgin cement use. Each is a verified advance. But stacking them into a single miracle, free houses printed from garbage in 2 days, serves clicks, not understanding. Separating the verified from the exaggerated is not skepticism for its own sake. It protects the real achievement from the backlash that follows every broken promise. The genuine story does not need embellishment. So what does the honest, combined picture actually reveal about where China's construction is heading? To answer, we must weigh policy, engineering, and automation together. Step back from the headlines and a coherent picture emerges. Less spectacular than the viral version, but far more consequential. 3 forces are converging. First, policy. The 2025 national directives pushing prefecture-level cities toward 50% construction waste utilization by 2027 created demand where none reliably existed. Targets, subsidies, and reporting turned an abstract environmental goal into an industry with buyers, sellers, and accountability. Second, engineering. The technical standards taking effect in 2025 and 2026 for recycling equipment and aggregate quality gave that industry a common language. A recycled block or panel can now be specified, tested, and trusted because the numbers behind it are defined and enforced. Weaker recycled aggregate is not pretended into strength. It is measured, blended, and placed where its properties fit, from road base to non-structural fill to partition blocks. Third, automation. Construction printing, prefabricated panels, and factory production are compressing timelines and cutting waste at the source, so tomorrow's demolition generates less debris to recycle. None of these forces alone transforms construction. Together, they form a loop. Buildings come down, their material is crushed and certified, remade into blocks and base and panels, and installed in the next generation of structures. The loop is still leaky. Recycled content remains capped, viral claims still outrun reality, and much rubble is still landfilled. But the direction is unmistakable and, crucially, verifiable. What makes this durable is precisely the discipline this film has insisted upon. The projects that will last are the documented ones: the Beijing paving, the Shenzhen subbase, the Zhonggan pilots, each with test certificates and traceable percentages. The Shanghai printed house matters not as a myth of free construction, but as a genuine demonstration of what machines can build. Honesty about the limits is what allows the achievements to endure. A nation that once measured demolition in mountains of waste is learning to measure it in tons of raw material, redirected before it reaches a landfill. The concrete of yesterday's buildings is being crushed, tested, strengthened, and poured into the roads and walls of tomorrow. In China's recycled construction future, the lesson is deliberate and structural. Waste is becoming the foundation.